Hello and welcome. In this lecture, we will see some problems and their solutions in the chapter Units and Measurements. In this example, we are required to convert 0.5 meter per second into kilometer per hour. Now we know that 1000 meter is equal to 1 kilometer and 3600 second is equal to 1 hour. Therefore, 0.5 meter per second becomes 0.5 meter per second into 1 kilometer by 1000 meter into 1 hour by 3600 seconds inverse. This becomes 0.5 into 3600 divided by 1000 kilometer per hour, which is equal to 1.8 kilometer per hour. In this example, a new unit of length is chosen such that the speed of light in vacuum is unity. We are required to find the distance between the sun and the earth in terms of new unit if light takes 8 minutes and 20 seconds to cover this distance. So we are given that in the new unit of length, c is equal to 1 unit length per second. Time taken by sunlight to reach earth is t is equal to 8 minutes 20 seconds. This is equal to 500 seconds. Therefore, distance between earth and sun in new unit of length is equal to c times t, which is equal to 1 times 500. Therefore, distance between the earth and the sun in the new unit of length is 500 unit lengths. In this problem, we are required to find the value of this expression. Each number in this expression has two significant digits and they are represented in scientific notation. Since only multiplication and division is involved, we can group the base terms together and the exponent terms together. Therefore, grouping the base terms, we get 5.0 times 6.0 divided by 1.5, and grouping the exponent terms together, we get 10 to the power minus 4 times 10 to the power minus 4 divided by 10 to the power 3. Arithmetic operation on base terms gives result 20 and exponent terms gives 10 to the power minus 11. Therefore, the value of this expression is 2.0 times 10 to the power minus 10. In this problem, we are required to evaluate few expressions using significant digits. The first expression is 3 times 10 to the power 2 plus 4.1 times 10 to the power 3. The next expression is 7 times 10 to the power minus 2 plus 2 times 10 to the power minus 3. The third is 4.76 times 10 to the power minus 2 minus 4.81 times 10 to the power minus 2. The fourth is 5000 times 0.005 and the fifth is 5000 divided by 0.005. In the first expression here, we have first term as having one significant digit and the second term having two significant digits. Therefore, the final value will also have one significant digit. To add, we have to match the exponent terms. Therefore, 4.1 times 10 to the power 3 can be written as 41 times 10 to the power 2. Adding the base terms, we get 44 times 10 to the power 2, and dropping off the insignificant digit, we get 4 times 10 to the power 3. In the second expression, we have both terms having one significant digits. So the result will also have one significant digit. Now to add, we have to match the exponent terms. Therefore, 7 times 10 to the power minus 2 can be written as 70 times 10 to the power minus 3. Adding the base terms, we get 72 times 10 to the power minus 3, and dropping off the insignificant digit, we get 7 times 10 to the power minus 2. In this third expression here, we have both terms having three significant digits and the exponent terms are also matching. Therefore, taking the difference of the base terms, we get minus 0.005 times 10 to the power minus 2, which is equal to minus 5.00 times 10 to the power minus 5. Both terms in this fourth expression are having one significant digits. Therefore, writing in scientific notation, we get 5 times 10 to the power 3 times 5 times 10 to the power minus 3. This is equal to 25, and dropping off the insignificant digit, we get the result as 20. The last expression here is 5000 divided by 0.005. Both are having one significant digits. Writing in the scientific notation, we get 5 times 10 to the power 3 divided by 5 times 10 to the power minus 3, which is equal to 1 times 10 to the power 6. In this problem, we are given a physical quantity having relation f is equal to a cube. We are required to find the relative error in f if relative error in a is delta a. We can write f is equal to a cube as a times a times a. Now we know that when the product of terms is involved, the relative errors gets added. Therefore, delta f by f is equal to delta a by a plus delta a by a plus delta a by a. Therefore, relative error in f is 3 times relative error in a. So we can form a general rule. The relative error in a physical quantity raised to the power n is n times the relative error in the individual quantity. This is a problem on dimensional analysis. A simple pendulum oscillates under the action of gravity. Suppose that the period of oscillation of the simple pendulum depends on its length L, mass of bob m, and acceleration due to gravity. We are required to derive the expression for its time period using method of dimensions. So we are given that time period of oscillation is equal to k times m to the power a times L to the power b times g to the power c, where k is a dimensionless constant and value of a and b and c are required to be determined. Introducing dimensions for t, m, l and g, we get m to the power 0, L to the power 0, t is equal to m to the power 1, L to the power 0, t to the power 0 to the power a, m to the power 0, L to the power 1, t to the power 0 whole to the power b, m to the power 0, L to the power 1, t to the power minus 2 whole to the power c. Grouping the same dimensions together, we get m to the power 0, L to the power 0, t is equal to m to the power a, L to the power b plus c, t to the power minus 2c. Comparing power of base dimensions, we get a is equal to 0, b plus c is equal to 0, and minus 2c is equal to 1. Solving for a and b and c, we get a is equal to 0, b is equal to half, c is equal to minus half. Using the values of a, b and c in this relation, we get time period for oscillation t is equal to k times L by g to the power half.